All right, I think we should get started. I'll record it too. All right, great. So today I wanted to move on to applications that are more relevant for geometry. And our next example is a category of spans, or more precisely, I should of course say it's not really a category, but it's more like a, even in the simplest possible case, it will be 2, 1 category. Meaning you have objects, you have morphisms, you have objects, you have one morphisms, and you have invertible two morphisms. So here's how it works. The input this construction is a category C with pullbacks. It admits pullbacks and the terminal object. So that's equivalent to admitting finite limits. And we construct span C, which will be a 2, 1 category. Its objects will be the same as objects of C. And morphisms between two such objects will be what is called span, as spans. So this is called a span. You can kind of see it's like a span of a bridge, for example. And here you have another object in the category mapping into both your source and target. Since I promised some relevance for geometry, one way to think about this geometrically is that here A01 maps to the product of A0 and A1. And for example, if this map is a monomorphism, it could be a monomorphism, for example, then you would see some geometric shape inside a product. And that's called a correspondence in geometry. And in some situations, like the Weinstein category of Lagrangian correspondences is very relevant for symplectic geometry. So that's this example has a very physicsy flavor. Okay, so how are two such morphisms composed? So here is one morphism given by one span. Here is another morphism given by another span. And the way we compose them is we take these two middle maps and we complete them to a Cartesian square. This Cartesian square exists because our category has pullbacks by assumption. And then we then maybe I should have drawn a picture here. The resulting composition will be this span. One arrow and the other arrow. Oh, yep. That's how you compose spans. Again, geometrically, I guess you could call it convolution or similar, or perhaps intersection in some contexts you could call it. So in principle, that's oh yeah, and of course I should mention a physicsy example where you say that A0 and A1 are spaces of fields on bordisms. And those of you who are attending our quantum homotopy seminar know that these spaces of fields should ultimately be smooth sets. And then A01 will be so A0 and A1 will be spaces of fields on some source and target of a boardism, and A01 will be a space of fields on the entire boardism. And then these two maps will be restriction maps. A field on the entire boardism, or a function, for example, on the entire boardism, can be restricted to its source and its target. And here we immediately see a problem with this current definition because composition, as we define it, is only defined up to a unique isomorphism which is not, there is no canonical way to choose it. And there are many solutions to this. Of course, the very traditional solution is simply to take isomorphism classes of such spans and declare them to be morphisms. But if you are familiar with the ideology of higher category theory, you will recognize that this is not going to be an interesting solution because typically taking isomorphism classes or passing to the homotopy category in such a situation is usually a bad idea because you lose too much information. So instead, we are going to try to encode this 2,1 category as a single object. So in our case, of course, well, previously we talked about single objects in simplicial sets, but here these simplicial sets will all be nerves of groupoids. So really this will be a single object in groupoids. Okay, so here's how it works. Span C will be a functor from delta op to groupoids. And as I said, if you want, you can compose it with a nerve functor to get something that lands in simplicial sets. And its value on some n, on some simplex n, will be a groupoid. And objects in this groupoid will be commutative diagrams of indicated shape. So here I drew an example for, well, I guess this is an example for a generic n. But in principle, this part that you see here will be an example for n equals 3. And so it will be a commutative diagram of this shape. As you can see, it's just a pyramid. And every little square in this pyramid has to be a Cartesian square. So all these squares must be Cartesian squares. So that's what an object is for an object in the groupoid of n simplices. And morphism will be an isomorphism, and more precisely, it will be a natural transformation. It will be a natural transformation which is invertible, so its components are isomorphisms. And we furthermore require that on the bottom row, so these bottom rows, we get identity. So the bottom row is not transformed. Only the other rows are allowed to be made isomorphic to something else. Yeah. Okay, so that's how you define the groupoid. And in particular, you can see that if you restrict to the case n equals 1, so a single span, you will see the groupoid of spans and their isomorphisms, where isomorphisms simply act on the middle object. Now, in order to define a single space or a single object in general, I also have to tell you not just the value on objects, but also how simplicial structure maps act. And in this case, well, face maps will be relatively easy. You will simply delete a shape, so to say, from your diagram, which looks like, well, that's my attempt to depict what it looks like, but let me also, for example, imagine you want to delete the first face, right? So you will delete these guys. You will remove them from the diagram altogether, and you will compose pairs of arrows that sort of have to go through it, right, like this. And this will give you an object in the groupoid of simplices of n-1 simplices. And of course, the case of outer face maps will, as usual, be special. For example, for the zeros face map, it will simply delete the leftmost diagonal. Now, simply show degeneracy maps, as usual, they will insert what in our case will play the role of a monoidal unit, which is simply the terminal object. So the terminal object exists because our category has pullbacks. Well, I should have said pullbacks in the terminal object, of course. And so this is what you are going to insert in some position. And then it's easy to construct the corresponding Cartesian squares by duplicating um, the relevant data. So for example, let me give you one example of a degeneracy map for a single span. Let's say single pair of spans. Oh no, this is too much. Say if I duplicate the first vertex, yes, sorry, not duplicate, but apply the degeneracy map to the first vertex, what I get is a0, a1. This is going to be a mess. So if I apply the first degeneracy map, then I will here I have going to have the terminal object a1, a2, a0 here. Yeah, so let me draw a bigger picture maybe. Oh, much better here. So here's our original. Much better. Let's clear as Cartesian. So if I apply the degeneracy map, say, because the first vertex, this means I would have to insert the terminal object in this position. So it's going to look like a0, terminal object, a1, a2. And now I construct the obvious Cartesian squares. Everything sort of tautologically fills out. Because everything is pretty much canonical. Some maps are eigenvalent, and that's perfectly normal. Yeah, so here's how a degeneracy map works. All right, that completes our definition. Any questions about the definition of the Siegel object of spans?
There is a question in the chat.
That question. Oh yeah, sorry. Was what? Why is the identity condition on the bottom row? Oh, if we allow the isomorphisms there, we get an equivalent true comma one category. Oh, you mean why we insert the specific object? Well, we have to insert something, right? I mean, it's simply for the reason that if you apply a degeneracy map, based on our definitions, we do expect to see some object here, so it has to be a choice. Has to be a choice. Oh, maybe you were talking about this one, I think, yes. So identity on the bottom row. Let's see, if we also allow isomorphisms for the bottom row, let's see, maybe we should have, I mean, I'm not sure if I got it right, one moment. Yeah, so of course, and this actually will be example, I should have, I'm going a bit ahead now, but if you remove this condition, you will get an equivalent category, and this will be what is called a Siegel completion, or a complete Siegel space equivalent to the given Siegel space. So let me comment on this a bit later. When we, in about 10 minutes, we'll switch to complete Siegel spaces, and there this comment will become relevant. Yeah. Yeah, exactly. So the groupoid of spans is precisely the groupoid of functors and natural transformations from a diagram of this shape, where you impose two additional conditions. The first additional condition is that these squares must all be mapped to Cartesian squares. And the second condition that I imposed for this definition is that on the bottom row, your natural transformations are identities. So that's the one morphisms and the two morphisms, respectively. Yeah, so it really is basically a category of functors and natural transformations. Yeah. Yeah, if I don't see a question, just tell me I have a question, because sometimes I will be looking at my notes and I may not see a question for a while. All right. Any more questions about the Siegel object of spans? All right, since I promised more examples from geometry, since here's another example. What happens if we take spans, but in the opposite category of, say, the opposite category of spaces? Well, then what used to be a span is now a cospan. The arrows will point toward the object and not away from it like previously. So here in all those pictures, the arrows will start pointing in the opposite direction, and the Cartesian squares will become co-Cartesian squares. So instead of pullbacks, you will have pushouts. And here's an example of such a co-span. It's any boardism will give you a co-span. So here's a typical example of a boardism from two red circles to a single green circle. You see the total space of the boardism is a topological space. And you have two inclusions of the source, inclusion of the source, and inclusion of the target. And the operation of composition of spans, or in our case, co-spans, now acquires a geometric meaning of its own. If you have a co-span here, given by some boardism, and another co-span with a compatible domain here, which is another boardism, and then you start composing them, and you compose them by taking these two arrows, and completing them to a push-out square. So here is a push-out square. This square is a push-out. Well, I can indicate this is a push-out square. And you see this, since the middle object has to be identified in both copies of boardisms, the boardisms are going to be glued here at this edge. So composition of co-spans is literally composition of boardisms. And of course, those of you who have some experience with this will notice a defect. The defect, of course, is that such naive gluing as I performed here is only going to work with, say, topological boardisms. Meaning, if you glue topological manifolds, it's fine to glue them using just an ordinary categorical pushout in a naive sense. So that will always give you a topological manifold. But everything else is going to be more difficult. So, for example, if you have a Riemannian metric on your boardisms, then this gluing is simply not going to work. Yep. All right. Any questions about spans or co-spans before we move on to completeness of single spaces?
Please, may you repeat about some physical intuition behind all this spans and co-spans?
Well, the canonical integration here is that boardism is just, if you want, a space-time. And the simplest example of a boardism is a cylinder. So here's maybe a cylinder. A cylinder of some length t. And you interpret the cylinder of length t as a space-time. So t will be a time coordinate, and the sourcing target will be some space-like surfaces, or a Cauchy surface inside a space-time. So that's one interpretation of a boardism. It's just a time of a space-time along which you want to evolve, and then the co-span picture arises. The span picture, so that we considered previously, arises when you start considering fields on such spacetimes. So the simplest example of a field will be a smooth function on such a spacetime. And such a smooth function on the entire spacetime will restrict to its source, giving a smooth function on the source, and it will restrict to the target, giving a smooth function on the target. And so you see you have now a span where you have here the space of smooth functions on the entire bordism, and here you have a space of smooth functions on the source, and here you have a space of smooth functions on the target. So that's interpretation is that sourcing the objects in your category can now be spaces of fields, for example, or vector spaces more generally, and then morphisms will be some kind of vector space that maps to them both, and you think of it as a restricting a space of fields on a bordism to its source and target.
It is also maybe considered as some kind of field, yes? A with 0, 1, and A with
Yeah,
1
A01
and
should be considered as a field on the entire bordism, on the entire space-time, yes. Yes.
these are spans, yes? And what's about cospans? Cospans?
Yeah, cospans, what we had previously, cospans are just the bordisms themselves. Here we previously had an example of a cospan where you have a bordism. So here's your space-time, and the source and target include as, for example, as smooth manifolds.
In this example, yes, as I understand, circles, yes, are considered as a field, yes?
So here a surface is really a Cauchy surface. And this, the whole cylinder is a whole space-time. And you think of the cylinder as it connects to Cauchy surfaces in a space-time. And if it is a cylinder of length t, then you think of the cylinder as corresponding to a time evolution for time t. So, for example, if you have when you apply a functorial field theory to such a bordism, the source and target will get mapped to some vector space of skates, and the cylinder itself will get mapped to some time evolution operator with respect to time t. So in particular, if you take now the derivative with respect to t, you will get the Hamiltonian of your physical system.
Mhm.
Okay, we also have a question in chat. There is also an infinity and category of spans. Sorry, is it possible to use it to define bordism categories? If we let C to be smooth sets. Well, yeah, I mean, of course, that's the direction we are moving. So it's we will be eventually defining some version of infinity n category of cospans, more precisely bordisms. And of course, yes, it will be in particular, among other things, valued in smooth sets, or in fact, something even more general than smooth sets. It will be simply show smooth sets. So, yeah. So in general, yes, of course, the answer is positive, and we will see how it works maybe just a bit later. All right. If there are no more questions, let me now talk about the completeness condition for Siegel categories. And the completeness condition addresses the following problem. So let's say we have a Siegel object in simplicial spaces. But again, if we want to stick to the simplest possible examples, it's already fine to consider Siegel objects in groupoids. The phenomenon of completeness is perfectly visible for simplicial objects in groupoids. And with this description, we have a redundancy. We have two different notions of an invertible one morphism. Because the first notion is you take the groupoid of one simplices, and you take extract the subgroupoid of invertible one simplices, and say an object in this groupoid can be perceived as an invertible arrow. And there is another potential candidate for the notion of an invertible morphism, which is if you just pick a one simplex in the simplicial set of objects x0, that's also a potential candidate for invertible one morphism. So slightly more precise, we have a canonical map from x0, which is if you want a space or a groupoid or infinity groupoid of objects. And we also have x1 cross, which is a sub-object of x1, where you pick only those connected components of x1 that correspond to invertible arrows under composition. And there is the zeros simplicial degeneracy map, which you think of really as sending an object x, well, maybe I shouldn't say x, sending object A to the identity arrow on A. This gives you a map from one to another. And in principle, both sides, left and right, can be thought of as expressing invertible morphisms in your X. So a Siegel space is called complete if this map, the map star, is a weak equivalence. By the way, is there any need to remind you guys how the definition of a cross, so this cross where I said extract the invertible part of x1, are you guys now comfortable with extracting this invertible part yourself, or is there any desire to see perhaps a recollection on this? Any opinions in either direction? Do we
Maybe
want?
quick recollection, if it's
Yeah,
possible.
okay. Yeah. So let me just offer you a brief reminder. So first, let's recall how, let's say we have x, simplicial object in simply show set, or as I said, it's also fine to assume, for example, a simply show object in groupoids, or even sets to some extent will also work, I guess. So what does it mean? So you think of X0 as infinity groupoid of objects, meaning its objects are objects of X, and higher morphisms are all invertible maps between objects. So this part only captures isomorphisms between objects. Then there's a X1, which is a groupoid of morphisms. And morphisms don't have to be invertible. X1, as its objects, has also non-invertible arrows. So you may now recall the how morphisms are composed. So I have first of all true simply show maps from X1 to X0, which in traditional simply show setting will be called D1 and D0, but more traditionally we'll call them source and target. So you think of an arrow being a one simplex. A one simplex defines a morphism that goes from its zeroth vertex to its first vertex. So the map D1 removes the first vertex and therefore extracts the source. And we now can form the space of compatible or composable pairs of morphisms. So here I guess the source here has to coincide with the target here. And the signal condition tells us this accepts a weak equivalence from X to where the true maps to X1 will be the maps that take a true simplex. So here is an example of a true simplex. So if I remove the vertex true, I get the map F, and if I remove the vertex 0, I get the map G, and these are the true composable maps. So this map here is true components will be the map that removes the second vertex and the zeroth vertex respectively. And finally, there is a map that removes the first vertex, and this will be the map that extracts the bottom arrow. The bottom arrow you think of as some kind of a composition that depends on the choice of a true simplex. So now that we know how composition works, we can easily extract the part of X1 that is invertible with respect to composition. So first of all, it has to be a left and right invertible. So for example, how to extract something that is invertible in one direction. Well, a morphism is invertible in, say, a left invertible if there is another morphism, so that their composition is identity or isomorphic to identity. So what we can do here is inside X1, I can take, let's see, well, let me give you a naive construction. So inside of X1, I have a sub-object given by the connected component of the identity. I'm not even sure what to call it, but let me just put a little superscript ID for identity. So this is just a subgroupoid of X1 given by the connected component of identities, or in our case, it will be identities. I guess you can also say maybe a bit more precise. Let me be a bit more precise. So X0 degenerates to X1. The degeneration map sends an object to the identity morphism. And inside here, the essential image of this map is precisely the connected component of identity. So maybe I can write it like this. So X1 identity is a full subgroupoid of X1 on objects in the image of S0 and objects that are isomorphic to those objects. So now I can form a pullback here, and form X2 identity as a pullback. And geometrically, this simply means X2 identity is the groupoid of those triangles where G composed with F is isomorphic or homotropic to identity. So that's the meaning of X2 identity. Now, this map here is a weak equivalence, and this map is an inclusion of connected components, because X1 identity was such an inclusion. So I can transport this inclusion along this weak equivalence, and I get some inclusion here. Well, let me literally just take the composition here. So this arrow is simply the composition of these two arrows. So the image here is going to, you are going to think of it as the groupoid of pairs f comma g, such that the composition f composed with g is homotropic to identity. So morally, here we have pairs, well, G comma F, if we respect the ordering, for which the composition is homotropic to the identity morphism. And so what we can do now is we can take the projection map. projection map, say, to the first component. So it will send, morally, it just sends G comma F to F. This is just second component, I guess. So this is just a projection map. And now the image of x2 inside x1. So this composition will, as its input, it will take a pair f comma g's, so that f composed with g is homotopic to identity, then it will send it to f. So this is just a funny way to say that the image of this map will be the space or the groupoid of f's that are invertible from the left, I guess. So they have a left inverse. So the essential image here, you should think of it as a space of f, or the groupoid of f for which there is a left inverse. Meaning this composition is identity or homotopic to identity. Now we can do exactly the same trick for right inverses, and we can intercept the two images inside x1. And so this will be the space of morphisms that have both a left and a right inverse. That will be exactly what we are looking for. So this may seem a bit involved, but it's basically not much really is happening here other than we are translating the usual definition of a invertible morphism into the language of Siegel objects. And maybe I should also mention one more alternative description as a remark. Both may be more concise, but not necessarily more comprehensible. But in fact, another way to think of x1 cross is as a space of maps from the nerve of a free walking arrow, or more precisely, free walking invertible arrow, to x. So this is just essentially the usual nerve functor. It turns a category or a groupoid into a Siegel object. And this category here, I mean, a bit more precisely, it will be a category with two objects, 0 and 1, and two non-trivial isomorphisms between them, with all the other compositions being identity. And of course, morally, you think of this as encoding, so a functor out of this category to some other category C is going to pick two objects in C, an arrow from 0 to 1, and its inverse. So that's just saying you basically are picking out an invertible arrow. And that's another way to describe the space of invertible arrows. Maybe that's a bit more concise and but not necessarily more comprehensible. So the elementary description above, maybe it's in some sense more hands-on and more concrete. Okay, any questions? Okay, so let me go back to the definition of completeness. So completeness means the map from the groupoid of objects to the groupoid of invertible one simplices is a weak equivalence, which means that if in the case of ordinary groupoids, it will be an ordinary equivalence of groupoids. In the case of simplicial sets, it will be a simplicial weak equivalence. So let me give you guys some examples of complete and non-complete Siegel objects. And perhaps the easiest example of a non-complete Siegel object will be the usual nerve of an ordinary category. Let's recall that in this construction, the usual nerve, the n simplices of the nerve form a set, a discrete set. Elements of this set are functors from this category, if you want, where you have n composable arrows, and you have a functor from it to C. So in other words, an element of this set is a collection of n composable arrows in C. So in particular, x0 will be functors from just 0 to C. In other words, it will be just the set of objects in C. Whereas, for example, x1 will be functors from 0 to 1 to C. So this will be just a set of morphisms, just a set of morphisms in C. And of course, x1 cross will pick out isomorphisms. So x1 cross will be the set of isomorphisms in C. So the zeros degeneracy map from x0 to x1 cross will take an object in C and send it to its identity morphism. So this will be a map of sets, a map of discrete sets. And this map is typically not a weak equivalence because in order to be a weak equivalence of discrete sets, you must be an isomorphism of sets, a bijection of sets. And as soon as C has isomorphisms that are not identities, you are not going to see a bijection. So this is not a bijection. Let me point out if C has non-identity morphism, non-identity isomorphisms. Or in other words, non-trivial automorphisms for objects. Okay, so this example is not a complete Siegel space. Let me now also give you now a variation of this example that is complete. So that's called the Resk nerve. And it's actually very similar in spirit to the nerve, but now you say I start with the same data, so I should have probably mentioned that C in here is a category. C is a category. Yeah, there's a question in chat that asks, I guess, about x1 cross. If we can define it as F, the collection of F such that there's a G, so that FG is homotropic to identity and GF is homotropic to identity. Yeah, it does give you an equivalent groupoid. So I guess one question that was raised here is, a priori, we can have a separate choice of a left inverse and a right inverse. And you may be wondering if forcing those choices to be the same could possibly alter the space of invertible one morphisms. And the answer is it does not. So in fact, turns out it could be a weakly equivalent space. So forcing the left inverse and the right inverse to coincide will not change anything in your space. No, the corresponding coherence problem is actually trivial in this case. So you can also see it. Well, maybe I should be more careful in my statements. So let's see. All the coherence can be moved out to higher simplices. So completeness is also called completeness in homotopy type theory, actually. So univalence is a special case of completeness when you apply completeness to the category, basically to your universe. But in general, it's the same term. So in general, you will talk about completeness. So univalence is just a special case of completeness applied to the whole category of types. The reason in homotopy type theory you want to formulate the existence of left and right inverse separately is because like here you see, like in homotopy type theory you would not be able to easily express what I wrote in this concise definition here. So this is not expressible in homotopy type theory because there is no way to talk about simplicial objects in homotopy type theory. So this definition that express it very nicely and elegantly as a mapping space from this groupoid to X is just no easy way to formalize it currently in homotopy type theory. And that's why you have to use ad hoc tricks, like the one mentioned in the chat, where you would have to it's kind of similar actually to this elementary description here. So this would also be roughly the homotopy type theory definition, where you separately require the existence of a left and a right inverse, which avoids the problem of formalizing this definition here. Only the elementary definition we know how to formalize in homotopy type theory. And that's why, so the fact that we don't, that we separate left and right inverse in homotopy type theory is not, it's not some kind of intrinsic difficulty. It's just that the language is not rich enough to express this definition right away here. So it's more like a defect of homotopy type theory in its current formulation. Yep. Okay, so let me finish the description of the rest nerve. So in the rest nerve, you take the same functors from the same category to C, but now you take not just a set of functors, you take the groupoid of functors. So in addition to taking the functors themselves, you also pick their natural isomorphisms. These will be isomorphisms in your groupoid. So Xn is now a groupoid. For example, you can say x0 will now be not just the set of objects in C, but rather it will be the whole groupoid of objects. So its objects will be objects in C, and isomorphisms will be invertible maps. And likewise, x1 will be the groupoid of morphisms. So its objects will be morphisms in C, and isomorphisms will be commutative squares. So here is one object, here is another object, and then an isomorphism between them will be a pair of invertible arrows, like this. And in particular, x1 cross will be a groupoid whose objects are isomorphisms in C, and morphisms will be invertible, pairs of invertible vertical arrows. So it will be commutative squares of isomorphisms. And in particular, the degeneration map as 0 from C cross to the groupoid of isomorphisms in C. This map will send an object in C to the identity map on this object, and an isomorphism in C cross will be mapped to a commutative square, where this isomorphism appears as vertical maps, and the horizontal maps will be identities. All right, any questions about the definition of the RESC nerve? All right, let me now explain why actually the RESC nerve is complete. So that's what is going in part A on the left side. So as I already described for you this functor S naught from C cross to isomorphisms in C. Maybe I should match the notation. I'm not sure why the notation suddenly changed. So to show that this functor that sends C cross to isomorphisms in C is an equivalence of groupoids, let's just see that it's fully faithful and essential surjective functor. And let's start with essential surjectivity. So essential surjectivity tells us if I pick an object here in this codomain category, so that's this F. So an object here is an isomorphism in C. Let me call it F. I have to demonstrate to you that we can find an object in the domain, which is C cross, whose image under this functor is isomorphic to F. And here's how you do it. So let's say F is an isomorphism from X to Y. what I'm going to do, I'm going to pick x as my object in C cross. So the functor sends x to the identity x. And now I have to construct for you an isomorphism from identity x to f. And here, this isomorphism is a pair of vertical maps given by identity on x and f. And you can see the square commutes. This establishes essential surjectivity. And fullness and faithfulness is even easier. So fullness demands, it says, if I have two objects in the domain category x and y, and I have a morphism between their images in the codomain, so their images in the codomain will be identity x and identity y. And if I have an isomorphism, or in general, a morphism between their images, so in our case, it will be a commutative square where the vertical maps are isomorphisms. And notice that because the horizontal maps are identities, this forces the two vertical maps to be the same. And I have to show to you that such a morphism between their images is in the image of this map as 0 from left to right. Indeed, if I simply take the same f as my morphism here, its image under S0 will be precisely this commutative square. And so the only thing we use here is that the two vertical maps must coincide. And of course, from this description, you also immediately see that this functor is faithful because different f's will map to different morphisms here, different commutative squares. Yeah, so this shows this functor is fully faithful and essentially surjective, and therefore the rest nerve is complete. And I guess I will leave it to you as a little simple exercise to prove that the rest nerve is also a Siegel space, or more precisely, complete Siegel object in groupoid. In groupoids. As a little exercise, you can prove it is a Siegel object, which is basically completely informal, but recommended nonetheless. And let me now. So, any questions about the proof of completeness? Right. Let me now very briefly address the sort of question of what exactly is the difference between the nerve and the rest nerve. And there's an inclusion map from the usual nerve to the rest nerve, which you kind of see from the definitions already, right? It's clearly the set of functors of this form will include as a discrete category into the groupoid of all such functors. So we are not going to touch morphisms, but we will hit all the objects. So that's exactly how this map works from the nerve to the rest nerve. Like, as you can see already, this map is very far from being an object-wise weak equivalence, right? Here you see that a discrete set of functors is included into the groupoid of all functors. So of course, this is very, very far from being a an equivalence of groupoids, right? A groupoid is almost never equivalent to a discrete set. So this inclusion is very far from being an object-wise weak equivalence. Nevertheless, it is a local weak equivalence in the left Bowles localization that we previously mentioned. Did I mention the left Bowles localization that gives you Siegel completeness condition? Let's see, one moment. Oops. Yeah, that's a little problem, I guess. Oh. I thought I did mention it, but maybe one moment. Well, I sort of mentioned it very briefly here in this line. Yes, I should have probably at least briefly mentioned how to implement the completeness condition as a left Bowles localization. Let me see. So complete left Bowles localization. That yields complete Siegel spaces. So let's recall how things worked out previously. We started with a category of functors from delta up to simplicial sets. We equipped it with, say, you can equip it either with a projective or injective model structure. It doesn't really matter at this stage. And then we performed a left Bowles localization with respect to Siegel maps. Siegel maps had this form. And the effect of this was that once we perform a left Bowles localization, once we formally invert such maps, the fibrant objects will necessarily now satisfy a Siegel condition or a locality condition in general, which means that X is a fibrant object if once we map both sides into X, you get a weak equivalence. So in our case, xm plus n will map to xm fiber product xn over x0, and this map will have to be strictly speaking, we'll get the homotopy fiber product here, and this map will be a weak equivalence. well, part of what you will get for a fiber object is that this fiber product will, of course, will be a homotopy fiber product. And turns out the same trick works for completeness. So for completeness, you will add one more morphism. So you have these morphisms, and now you will add one more, which is basically we'll use what we have done previously. So you will take the nerve of a groupoid with two objects and isomorphisms between them. So this will be a Siegel space, so it will be an object in this category. So the nerve will be a simplicial set, and the set can be turned into a simplicial set as a discrete simplicial set. This maps to the Yonaga of 0. So now X is a fiber object. If the map from X naught, which is what you get from the right side, to the derived map in space from the left side, into X is a weak equivalence. But previously we saw that this part is what we also called X1 cross. So the completeness condition is in fact can be very easily encoded by a left Bowles localization. And it gives precisely this sense, like I mean a weak equivalence here. So as you have seen, this map is not going to be an object-wise weak equivalence, but it will be a weak equivalence in this much bigger class of local weak equivalences in the left Bowles field localizations with respect to Siegel maps and completion maps. And let me explain how you can easily see that this is going to be a weak equivalence. First, let me introduce a bit of notation. Maybe I should first ask if there are any questions about the model structures and left Bowles field localization that gives you a completeness, the completeness condition.
Please repeat about the second equation, the two stars. So
The second equation. So which equation is the second equation?
where two stars? So I mean this. Yes, I mean this.
This one?
Yes.
Yeah, so being a fiber object amounts to being a local object. So being a local object amounts to saying you take the derived mapping space functor into X. Now, mapping the representable pre-sheaf of 0 into X by the derived Yonaga lemma is going to give you simply X naught, the value of X, the value of X at 0. And mapping this, the nerve of this groupoid, so as we have previously seen, somewhere here, oh yes, right here. Mapping the nerve of this groupoid into X is another way to describe X1 cross, the connected components of X1 containing invertible one morphisms and only them. So that means this map, when you apply the derived mapping space functor into X to this map, you will get a map from X naught to this X1 cross. This map will be precisely the map used in the definition of completeness. This map is just a map from x naught to x1 cross, which is induced by S naught. The degeneration map. And so performing a left Bala's recognition with respect to this map will enforce the completeness condition. Okay. Any more questions?
There's one in the chat.
Oh, yeah. Yeah, see, the problem is the chat doesn't scroll automatically. So when somebody asks a new question, the stupid interface doesn't move. Yeah. Okay, I found really structure for representing simplicial can be the most efficient. The model category infinity ones through this left. Yeah, I mean, of course, the read structure actually coincides with the injective here. So if you want, I can mention this a bit more explicitly. Where is it? Yeah, so of course, injective in this case equals read. This is a special case of a more general statement. So the category delta op is an example of what is called the easy ready category, or Eisenberg-Zilber ready category. And for such categories, the injective model structure on simplicial pre-sheaves coincides with the ready model structure. So in this case, injective really is the same as ready. Yeah. Okay. Let me now introduce a notation which I now recognize as a terrible notation. I'm not even sure what. Anyway, so I will need the following notation. And I just realized like it already conflicts with. Anyway, so if X is a Siegel object, so a functor from delta op to simplicial sets, and let's say N is a simplex, I can take this functor from delta op to simplicial sets, and I can take a simplicial set, one of those simplicial sets, and extract the set of n simplices here. So this is a function that here I denoted by x with a subscript n, which of course is terribly ambiguous because I mean it could also mean the evaluation of x at n, which I expressed here much more verbosely as x evaluating at n. So the point here is you have two arguments of delta up, this one and this one, and evaluation at n will substitute n as this argument here, whereas the subscript n will substitute n as this argument here. These two are completely different functors, so they require two different notations, and I guess previously I may have used, in fact, just recently I used a subscript as a notation for this, which is maybe terribly confusing now, but from now on, let me use this notation with a subscript as a short way to refer to this construction here that extracts. So this construction extracts the set of n simplices from every possible value of this functor. And so now we can make some observations. What happens if we take the RESC nerve and evaluate the RESC nerve also extract the sets of n simplices from the RESC nerve. And what exactly is the what happens if you take the RESC nerve and evaluate it on or extract the sets of n simplices? So what exactly is this object here? Maybe I should have probably. So n RESC C n. Well, if you evaluate it on some m, as we have seen previously, we should really think of it as take functors 0, 1 to m into C. Now take the functors and their invertible natural transformations. And then I want to take the nerve of this and take its n simplices. So that's what the RESC nerve is as a simplicial object in simplicial spaces. Now we can explicitly say what n simplices in this nerve are. N simplices in the nerve are chains of n composable morphisms. And each morphism is going to be a natural transformation of functors like here. So the n simplices here will look like diagram. Let me see. So A 0, 0, A 0, 1 goes to A 0, M. Now here's a single isomorphism in this groupoid as a natural transformation between two such rows. So these vertical maps are isomorphisms, unlike the horizontal maps, which are not. Now, if you have a chain of n such composable morphisms, that means you are going to get a whole grid of such, which will extend all the way down to the nth row, a n 0, a n 1, all the way to a n m. And again, the vertical maps are all going to be isomorphisms. The horizontal maps need not be. Now let's stare at this picture a bit more closely. So I mentioned I'm interested in the case when n is fixed. So n is fixed. N is fixed. So what can we see here in this picture? And if we start varying m, so we keep n fixed, and m now varies. What do we see in this picture? So we see n is fixed, and it's fixed. And now we see, okay, if we start varying m, we see like more columns or fewer columns. And it looks like kind of the nerve of a category, because each column is like an object now, and the a single row of horizontal maps will be a morphism. And this whole grid looks like a chain of m composable morphisms between such columns. So this is indeed the case. So n, if you take the RESC nerve of C, fix this n, this will be precisely the nerve of a category which I can describe maybe more concisely as a category of functors. So here, as an object, I need to get a chain of n composable morphisms. And that's exactly what I'm going to put here. 0, 1, 2, and so on, up to n. So all these guys are invertible. That's why I drew also their inverses here. And you map this into C. So you create a category of such functors and their natural transformations, which I no longer require to be invertible, so there is no cross here. It's just a category of all functors and all natural transformations. No need to take invertible natural transformations here. And that's exactly what is written here. The nth layer of the RESC nerve is a nerve of a category whose objects are functors that pick out chains of n composable invertible morphisms in C. And morphisms are natural transformations that need not be invertible. Now, having made this observation, here's another funny observation. The degeneration map from the 0th layer to the nth layer is induced by a map of corresponding categories, which itself is induced by pulling back with respect to this functor here. So if you degenerate a 0 simplex to an n simplex, this amounts to precomposing with this functor. So you simply substitute this functor in the first argument. And notice now, since this functor here, all these morphisms are invertible. So this functor is going to be an equivalence of categories because it is definitely surjective and it is fully faithful. Like if you pick any two objects, there is a unique isomorphism between them, and that's precisely the only morphism here. So this is an equivalence of categories, and therefore, when we start mapping this equivalence of categories into C, we equivalence of categories transform into simplicial homotopy equivalences of nerves. So this degeneration map is a simplicial homotopy equivalence. Interesting. And as a final step, so just to remind you, we are trying to show that the map from the ordinary nerve to the RESC nerve is a local weak equivalence in the left pulse localization. Maybe I should keep it here and yeah. As a final step before we prove the theorem, let me observe that the zeroth layer of the RESC nerve, if you look at what happens to this construction when n equals 0, if n equals 0, of course, you just see the vertical direction collapses. You have a single row. So you have a single object here. So you just see the nerve of C. So the 0th layer is just a nerve the zeroth layer is just a nerve of C. And previously we saw that all the simplicial degeneracy map, in fact, for the same reason, also all simplicial structure maps are simplicial homotopy equivalences. So what we can do now will be basically the oldest trick in the book in simplicial homotopy theory. Whenever you see a simplicial object, you know that this simplicial object is going to be its own homotopy colimit. And that's exactly what I wrote here. I took the rest nerve, I took its individual simplicial layers, which organize themselves into a simplicial object. And now I simply recall that the homotopy colimit of any simplicial object is itself. And we previously saw that in this simplicial diagram, all simplicial structure maps, well, here I just formulated for degeneracy maps, but the same is true for phase maps or any simplicial maps, really. All these transition maps are simplicial homotopy equivalences. In particular, there are any simplicial homotopy equivalence is going to be a weak equivalence in the model structure that we are interested in here, in the left Pavlov localization. And the homotopy colimit of a diagram whose transition maps are weak equivalences, and the diagram itself is indexed by delta op, well, the homotopy colimit of such a homotopy constant diagram is going to be weakly equivalent to the zeroth object in this diagram. So via this trick that says the homotopy colimit of a homotopy constant simplicial diagram is weakly equivalent to its zeroth object, you can now see that indeed the ordinary nerve is weakly equivalent to the rest nerve. And I think this is a good place to stop because what I plan next is a Siegel space just describing the actual category of Bordisms, and probably it's best to postpone it for the next time. So I think I'll stop here, and thanks for listening. And let's see if you guys have any further additional questions left.
What is the number of this lecture?
Oh, yeah. Good question. Yeah, I should have probably indicated dates. Yeah, this is supposed to be lecture 15. Let's see. I'm pretty sure, yeah, that's lecture 15. Today is February 11th. Oh, and by the way, probably most of you guys are already aware of this, but let me just advertise it again. On Tuesday, we have a talk, which in a sense is relevant for us, also for this class, because it's basically a talk that provides input data for Functorial field series. So let me just paste. I posted a link in chat so you can see an announcement. It will happen at 10 a.m. local time, so that's 1 hour later than we started today. That happens on Tuesday. So So Gregorios is a postdoc at NYU Abu Dhabi. So he is going to talk about how to use smooth sets to construct basically what is input data for the quantization construction.
Are these seminaries provided simultaneously with the homotopy theory seminarias?
That's a research seminar, yeah. That's different from. We only have a single research seminar. That's the one you see advertised here. So the other seminar is a student seminar. The Q and quantum homotopy seminar is a student seminar, yeah, meant to be run by students and for students. Yeah, a seminar by students, of students, and for the students. Yeah. All right. And I guess that's it for today. And thanks for listening. And let me now stop the recording. Stop sharing, and let's also stop the recording. And I guess I'll see you guys either on Tuesday or on Wednesday or next week on Sunday.